Hello, and welcome to the CPM webinar series. Today's topic is understanding the basics of screw design. My name is Christian Davis, and I'll be your moderator for today's event. With locations around the world, CPM is a leading global supplier of twin screw extruders, extrusion systems, high-performance replacement parts, ring extruders, thermal equipment, and supporting services. Our webinars are intended to service, support, and inform you about the latest technologies, maintenance methods, and trends in the industry. Presenting today's webinar is Daron Fraim. Daron has over 20 years of manufacturing experience in various industries, including thermoplastics. More than a decade of his work has been directly related to extrusion compounding using co-rotating twin screw extrusion technology. At CPM, Daron works closely with our customers to support their application needs with respect to machine configuration, screw configuration, technical training, and other process improvement initiatives. If you have any questions during the webinar, please type them in the questions field. If it's not answered, you will receive a follow-up response by email. Daron, I'll now turn it over to you.
All right, thanks, Christian, and welcome everyone to this month's webinar. This is a topic that hopefully you'll find valuable in understanding the basics of screw design. So we'll get into the outline. So what I'll do is I'll first go through a lot of the different types of screw elements. We'll take a look at some of the geometry. We'll go over the element's function in the process, and then we'll look at the unit of operations when we go through the extruder in terms of feeding, melting, mixing, degassing, and pressurization. We'll touch on some raw material factors to take into consideration, and then we'll look at some processing conditions. I have several examples that'll kind of show you a variety of different processes and some key features on some of the elements. And then I have a quiz at the very end, so Christian will help me there, and we'll take a look at that. So when you look at the different types of screw elements, I try to categorize these, and this is not, of course, an exhaustive list. There's a lot of elements out there. Some have some very unique geometry, some are special type designs, but these are your standard Erdminger type elements. The top being the standard conveying elements. You can see here I have a variety of design. The one outlined in red is a reverse conveying. But just to understand, these will come in forward or reverse conveying. Forward meaning conveying in the process direction or machine direction. Reverse meaning against the process direction. They come in a variety of pitch and length. Some are single, and most commonly your two flights. And then we have what we call the undercut conveying. These are what we classify as SK. Basically, there's some metal removed on the pushing side of the flight, so you add a little extra channel volume, usually 10 to 15% increase in volume approximately. One thing to note on these SK elements, these undercuts, is they are not 100% self-wiping. And then I categorize as transition elements. These can be transitioned from SK to standard and vice versa. Also single to two flight. And then also your two flight to three flight, even on your kneading blocks, these three flight eccentrics. And then, of course, there's a variety of mixing elements here. You probably recognize a lot of these being kneading blocks. Again, the one outlined in red is a reverse. Then we have a lot what we call slotted or gear type mixing. And then you can have, again, two or eccentric three flight on the kneading. Some of these we'll go through in detail. We'll understand what their primary function is in terms of type of mixing. Then you have your blister ring, there's an eagle, and we'll go through that in more detail. So just to understand what the pitch is, the pitch is the linear axial distance traveled when tracing the flight around 360 degrees. So you can see here I've got three examples to demonstrate when we look at this nomenclature and we say SE 60, 60 being the pitch, 60 being the length course, the pitch is equivalent to the length. It takes one full revolution. You go the full distance of the element. Then you have an SE 6030. It's 30 length, but to make that complete 360 revolution, you'd have to travel another 30 millimeters. So that's an SE 6030. And then there's a 4060. Again, you're traveling 2/3 of the full length to go one revolution to trace that flight around. So that's an SE 4060. Now the larger pitch obviously has larger channel volume, but also will yield greater axial displacement in the process direction per revolution. And then you have your smaller pitch, of course, yields less axial displacement, lower channel volume. And then your left hand, of course, is a restrictive element, forces material back upstream, creating a pressure gradient in the extruder. And when we look in comparison to the two flight versus single flight, one thing that's interesting is the single flight, considering this is the same pitch, 60 as the two flight, there is a little less overall channel volume in the actual single flight element there on the bottom, the SF. However, because it has the very wide flights, the material has to travel a greater distance in the process direction to transfer from shaft to shaft. So you get an increased axial displacement, and these elements are greater at pumping the material, or in terms of pumping efficiency or conveyance efficiency. When we look at kneading blocks, this is just a little bit of the nomenclature up on the right. When you say KB, represent a kneading block, 45 is the stagger angle. 5 is the number of lobes, 20 is the length, and then the RH, or right hand conveyance direction, which is in the process direction. And we compare these side by side and we look at the different lengths. They all have 5 lobes, 20 millimeter length, 40, 60. What's changing is the lobe width. And when you go from very narrow width kneading block, those are high distributive, low dispersive. The one in the middle is what we call intermediate or moderate distributive dispersive. And then, of course, your larger or longer kneading block with the wider lobes is low distributive, high dispersive. And we talk about the two types of mixing, and when we talk about distributive versus dispersive. Distributive mixing, the key thing here is you're basically splitting or dividing the melt to homogenize without high shear, and you're basically achieving this without reducing the physical size of an additive or droplet. So really the goal in distributed mixing is just to uniformly distribute the additive without reducing its size. Where dispersive is you're going to reduce the physical size of the additive. So when you're dealing with like mineral fillers, calcium carbonate's a very key one, talc. There's others. Typically you impart higher shear, and the goal is to reduce the physical size of the additive. This here just explains a little more detail of how that takes place when we talk about distributive mixing or dispersive mixing and which kneading block is utilized. And so you can see here is more of a visual. What's happening is your very narrow or short kneading blocks, they're very thin lobes. So what happens is a higher volume fraction of the melt divides and splits around the lobe, versus a small volume fraction is actually passed between the tip of the lobe and the barrel wall, where the peak shear or the very high shear is taking place. Whereas on the larger wide lobes, you can see here that the wider that lobe gets, the higher the volume fraction of melt is captured and wiped between the barrel wall and the lobe tip. So that's where, and you can see here on the bottom, we talk about shear rate. When you think of at a fixed RPM, what's going to change that shear rate is the clearance. And the clearance, of course, the barrel clearance between the tip flight and the barrel wall is the lowest or the most reduced clearance, and hence anytime you reduce that clearance, you increase shear rate. So your maximum shear, or your peak shear as we classify it, happens at the very tip of the element flight in the barrel wall. And so in the case of melt being squeezed or captured in that small clearance region is where your high dispersion is. Now, when we look at the kneading blocks in terms of the stagger angle, and we understand when we talk about leakage flow, and you can see here on the left, when you look at the end view, you notice as you increase the stagger angle, you increase the space or gap between the lobes. And so anytime you increase that space or gap, you allow more material to flow back upstream in what we call leakage flow. So obviously going from 30 to 45 to 60 to 90, you're increasing your leakage flow. And that's important because that's what changes residence time. The more material that leaks past that element back upstream, the more time it's going to spend in that localized region. This is the same concept, but in this aspect, we're talking about reverse kneading now. So with the reverse kneading, the goal is to force the material back upstream. But again, there's space between that lobe. Material's going to leak past it and go in the direction of the process flow. So again, same concept. If you want to think, okay, which one's going to be a more restrictive element? Which one's going to hold back the material better or more efficiently? Again, your 30-degree, because there's not much space between the lobes for material to leak past it. So as you go from 30 to 45 to 60, again, you'll see increased leakage flow. And in this case, leakage flow in the process direction because it's a reverse kneading. Now we look at gear type or slotted screw elements, your SME, screw mixing element, your ZME, TME, these all function the same. There's different types of geometries in terms of the size of the gear tooth, the angle, and so forth. But the main thing to understand here is these elements divide and redivide the melt multiple times over. Basically, when they're rotating, literally they're splitting the melt into like spaghetti strands. But because those teeth and those slots are very thin, they don't capture much material between the tips and the barrel walls. So they're low dispersive, very highly distributive. Again, anytime you're dividing and redividing and splitting the melt, you're just simply distributing. And so these work very well for like incorporating liquids of lower viscosity into the polymer matrix. They also work very well distributing glass fibers. So as many of you know, if you're doing glass-filled compounds for mechanical improvement in terms of mechanical strength of the polymer, these are great at really splitting that melt and homogenizing, distributing those glass fibers without physically damaging or reducing the fiber size to retain that mechanical strength. The eagle is a little unique. Again, it is a distributive element. One thing you'll notice, it has very thin flights, and it does have a slight cutout on the very edge. The only difference here, this eagle doesn't have multiple cutouts like the SME, the screw mixing element. It only has a cutout on the very edge. But again, with that slight cutout here, and I don't know if you can see my cursor, but it's right here where these join. This is where they cut out. It allows crossover mixing from one channel to the next, so you get some mixing. So not quite as distributive as your gear type because it's not splitting multiple streams over, but again, very thin flights. So a very small fraction is captured between that tip and the barrel wall. And on the blister ring, now this is a dispersive element. And the reason for that is because this element is solid all the way around 360 degrees. So what happens, it forces all of the melt to have to go past that. So it's basically like a barrier. And so all of the melt is forced over that And so there's no splitting anywhere. It has to pass through that clearance between that blister ring and the barrel wall. So it is dispersive. Normally these are very short, so it's a short residence time, so it does create a lot of pressure, a high shear, but they're very effective at breaking up particulates and gels. Now we'll take a look, we'll go through each unit of operations, and we'll look at feeding and what are some key things here. One thing we recommend typically, anytime you're feeding material, you want to utilize the maximum volume of your machine, of course. So you get good conveyance capacity. Taking material away at the point of entry downstream. Normally what's recommended is we recommend a pitch in the range of 1.5 to 2 times your diameter. So for example, here we have a 40 millimeter twin screw. I'm using 80 pitch elements in both my feed locations, so I'm 2 times my diameter. You'll notice the difference in the polymer pellets. In the main feed, I'm using SK undercuts. And in the side feed location, I'm using standard 80/40. The reason for this, and I've seen people use SKs in side feed locations, the only risk there is, remember, these SKs are not 100% self-wiping. So they're recommended in the solids conveying and not as much in the melt section, because once the melt, a lot of times, depending on the polymer, some polymers have a tendency to stick to the screw shafts more so than others. So if you're not getting 100% wiping, you risk some material stagnating in that area, in that dead space of that cutout flight. So if you're using SKs in the side feed, there is some risk that material may stagnate and potentially degrade. Again, the SE has a little lower volume, but main thing here is to understand, utilize the volume, use your higher pitch elements. Here we're looking at liquid injection. Pretty common to see most people inject into a conveying section. Some will inject into the mixing. Here's just a note, the difference in what's taking place here. You'll see here on the left, when you inject into a conveying section, your melt is a larger fraction, because that melt's filling those screw channels. And so you don't get quite as good surface area contact. Not to say it won't work, but there is somewhat of a pulling effect when you inject into that conveying element. Whereas if you inject directly into these ZMEs, you can see here on the right, as we talked about earlier, these gear type, they're very good at splitting that melt stream. Now you're injecting a lower viscosity liquid into a higher viscosity polymer, when that polymer is split into many smaller streams. So you get a much increased surface area contact with the polymer. So you get a quicker uptake of the liquid additive. Most commonly, your liquid adds are typically lower viscosity than the polymer in the main extruder that you're injecting into. But just know both will work depending on the length of your mixing section. Just understand, if you inject directly into that ZME, you'll get a quicker uptake of that liquid additive. One thing to note, though, when you do inject in the ZME section, that is a filled section, so you want to ensure your pressure, injection pressure, is sufficient to inject. Your pressure inside the machine is not greater than your injection pressure. When we look at melting, what's important to know on the polymer in terms of viscosity, as many of you know, typically when you purchase polymers, you get a melt flow. And melt flow is kind of an inverse indication of your viscosity. So lower melt flows are higher viscosity resins. And typically when you're working with lower melt flow resins, extrusion grade, and even down to fractional, you don't need a lot of melting length. You can typically melt that polymer in a shorter melting section. But then things change a little when you start adding higher melt flow resins or lubricants. Some of you may use like PE wax or other fatty acid type, lower molecular weight, lower viscosities. You may be injecting mineral oil. And so anytime you reduce that overall viscosity, there's less stress on the polymer. So when you're operating in a specific RPM, again, shear stress is dependent on both viscosity and shear rate. So at a fixed shear rate, if your viscosity is dropping or very low because you've added a high melt flow or a lubricant, now it takes longer to melt that resin. There you may get a delayed melting effect. So normally it takes, it could be a second melting section. So normally 2 barrels is sufficient after the main feed for your lower melt flows, but it may take 3 barrel sections, closed barrels after your main port when you're dealing with a lot of lower molecular weight additives. Now we look at melting and we look at the very first kneading block. And, this varies and it's really dependent upon the application. Most of you probably know, depending on the OEM of your machine, most OEMs offer kneading blocks that are what we call the short or narrow, and then the intermediates, and then the long or wide. And normally they will follow this general consensus that typically you're very narrow or short or around a half of the diameter. And then your intermediate, or what we call middle of the road, is usually pretty close to 1 times your diameter, and then your wide or longer are usually greater. So for example, here on the left where I note this, like on a 70 millimeter extruder, a 45-530 is going to be your narrow, your 45-560 is intermediate, and 45-590 is your wide. Now here on the top example, I've got a 40 millimeter twin. I'm using a 1D element. It is exactly 1D, being a 45-540. And normally we recommend starting with that nominal middle of the road kneading block. Unless you understand your application well and hey, I can get by with a different size. It's not a showstopper if you don't. But say, for example, a 45-520, because it's so narrow, remember it's primarily distributive, it's not capturing a lot of that polymer in the lobe between the lobe tip and the barrel wall. So it doesn't have a lot of dispersive or impart a lot of shear stress. Now this can, in the case of a fractional melt where your viscosity is really, really high, so if you're dealing with a 0.5 MFI, this may be sufficient to begin the softening of that polymer. So it's not to say you can't use a narrow one to start with. Same thing on the 45-560 being the large one. We normally recommend not to use that larger kneading block at the very beginning because it can impart a lot of stress on the polymer and could potentially degrade and create black specks. But again, if you're using a very low viscosity, maybe you have a very high melt flow resin, you're putting mineral oil, your PE wax, and your viscosity is low, you can probably get by with that element. So it really is contingent on the application. I always say it's a safe bet to start with the moderate or 1D kneading block is a safe bet. But and then 3-flight, I've seen some customers start out with 3-flight. We normally don't recommend them, not to say they can't do the job of melting, but mainly volume limitation. You lose a little bit of volume there. So when you're feeding that polymer in at the main port, leading right into that first element, you don't want to volume limit yourself. So the 3-flight can limit your volume. Now, when we think about melting, and when you look at this, and this is to show you the input and where the mechanical work is really happening, you'll see here that almost 80% of your work is put into that material in the melting section, the very first section to melt that polymer. And what it's done is it's taken That's the energy required to take that polymer from 25 Celsius ambient temperature to its softening, melting, and then melt it and bring it to process temperature. 80% of the work approximately is done there. And so if you're dealing with a situation where you're not sufficiently melting your resin, or the melt temperature is too high, this is where you want to change the screw configuration. Obviously, you can, if you're struggling to melt and so forth, normally first line of defense is to adjust the screw speed, and you can do that. But if you've made adjustments and it's not sufficient, you realize, hey, I've got to make a change in the screw configuration. Anytime you make a change in the screw configuration to improve melting or reduce melt temperature, you always want to go back to that very first section, because that's where majority of the work is taking place. If you make changes in the second, third, those downstream mixing sections, you're not going to see a big impact on changing the melt temperature. Again, I touched on this, but this is to give you a little more visual: distributive, dispersive. So when you think of distributive, the agglomerates, you're just distributing or homogenizing those uniformly throughout the polymer matrix. Where in dispersive, you're going to further reduce the physical size. So the type of mixing requires depending on the material application. So again, when we talk about mineral fillers, you want to reduce those agglomerates and the particle size, and talc as well. But with glass fibers, you want to distribute. So that will dictate which elements you choose and elect to use. So here, for example, I've got the top example is calcium carbonate, side feeding at barrel 5. And so you can see here in the first section, I'm distributing the calcium carbonate, and then my downstream, my very last section, is I'm dispersing the calcium. Now this is a debate on, okay, which one do you do first and what's recommended? Do I distribute first, disperse second, or vice versa? I always tell people that's a good exercise to do a DOE to validate that. But normally what's generally recommended is when you're bringing that calcium carbonate, you want to distribute it first. You want to wet it out and move it around uniformly into the polymer matrix, and then physically reduce its size. So typically, I will approach this and try to distribute that calcium carbonate and then disperse it. So in the glass fiber, the one thing that's changing, you'll notice I'm still using the same mixing section in the very beginning here with the 3 right-hand narrow and then the reverse. When you're working with glass fibers, many times they will be bundled together. I want to kind of debundle those fibers. So using those very narrow, small kneading blocks helps debundle and begin to break those bundles of glass up. But once those fibers are debundled, you can see my last section, I'm using all gear mixing with just the last narrow kneading block, reverse kneading block. So the idea there is to distribute those glass fibers without reducing the physical size. So I'm not using dispersive. So that's just to show examples, couple here that, hey, what type of screw design, what approach do I take is what you're trying to achieve in the process. And then, of course, higher loadings, when you're dealing with very high loadings of mineral fillers, you probably will utilize 2 side feeds. You can even put some in the main port. The thing to know on the calcium carbonate, anytime you bring in really, excuse me, high percent loadings, it will cool the polymer. So you don't want to get very, very high loadings in one location. You can crash cool that polymer. If you're bringing in 40, 45, 50%, you may overcool that polymer, stress it, and it may even solidify, and you can, of course, over torque your machine. What you'd have to do is go back upstream to your first melting section and increase that more in its aggressiveness to raise that polymer temperature to compensate for the drop in temperature when you're adding the calcium carbonate. And then below on the mineral oil, you can see here I'm coming in with a lower viscosity liquid. I'm injecting directly into that ZME, and I'm going to distribute the mineral oil. Now, it's not uncommon to see additives in the main feed port with polymer. These are your master batch type processors that may put everything in the feed port. The only thing here, I mean, it obviously can be done. It's not anything that's not recommended. This is pretty common. The only thing is you volume limit the machine when you stuff everything in the feed port. You will see increased wear in that initial melting, because remember, at the very first element, when you begin to soften and fuse that polymer, that's when it's at its highest stress, highest viscosity. And so in some cases, you'll see increased abrasive wear, but also you can, in some additives, depending on the particle size and the affinity between the particles, you may reagglomerate, because they're going through that very high shear or high stress region when that viscosity is at its maximum. You can actually compress, and sometimes you'll reagglomerate some additives. We look at degassing. Similar to feeding, you want to utilize your larger pitch elements. The reason for this, at a fixed speed, you want to have a low degree of fill to efficiently diffuse your volatiles. So you don't want highly filled channels in that region. You risk fouling the vent, but also you want the melt to be very, very thin or low fill, so you can efficiently diffuse the volatiles out. So again, use your 1.5 to 2 times your diameter type pitch elements under the vent location. And we look at degassing, we talk about atmospheric, vacuum vent. They're very similar. The only difference is, you'll see on the left, the atmospheric, I have a restrictive element. And when I talk about restrictive elements, as many of you know, it's a 90-degree or neutral kneading block. It's a reverse kneading, or it's a reverse conveying. Anything that restricts material moving downstream and holds it back, so to speak, and creates a pressure gradient. The only difference on the vacuum vent is you want to isolate the vacuum, so you want a pressure gradient on both sides of that vent, downstream and upstream. So here on the right, the example here is we're at the end of the machine, and of course at the end of the machine you have restriction due to the die or your melt filtration, your screen pack. You always get pressure at the end of that machine. So that pressure gradient is what seals that vent downstream. And so we'll see on the next one, when we talk about pressure gradient and how it affects in terms of what kind of vacuum level. This is important to know too. So if you're fouling your vacuum, it could be due to backup length on the end of the machine, material reaching to that vent location. But here in this example, we're going to look at the different restrictive elements and how much of a pressure gradient they create, because which element do you use there? And this is the very last element just upstream of the vacuum vent. Do I put a 90-degree kneading block? Do I put a reverse kneading? Do I put a reverse conveyor? This will really depend on your vacuum level, because you can see in the very top example with the 90-degree, I'm only getting a 0.6 bar pressure gradient to seal that vacuum. So if I'm running a very low vacuum, my negative pressure exceeds that positive. Then what's going to happen is I'm going to pull air through that machine. What's going to take place here, if this vacuum is too strong and overcomes this pressure gradient, guess what? I'm going to draw air through this vent here. I'm not sealing this vacuum. I want to isolate this region here when I draw that negative pressure. But as you can see here, as I move to my reverse kneading, look at the increase in pressure gradient. Now I'm at 1.25 bar. And then, of course, if I go to a reverse conveying, now I'm generating over 5 bar pressure. And so this is just something to note when you're fouling a vacuum. You're not sure why that's the case. You might want to take a look at this melt seal element here. Is it strong enough? Is it generating enough pressure, to seal that vacuum properly? Now, you may not know the actual pressure gradient like I was able to demonstrate on the simulation, but you could say, okay, well, I've got a neutral there. Let's move to a reverse. This is the progression I would take. If in fact you have a neutral element there, I would move next to your reverse kneading, and then if all else fails, to your reverse conveyor. Now, pressurization, you'll see this is pretty common on most machines, is you'll see a progressive reduction in pitch. What you're doing here is when you do that, you're filling those channel volume, you're generating pressure against the die. That's all you're doing. So it's pretty common to move from large pitch under the vent to start reducing your pitch down. There's no set rule on how far down do you go all the way below to a 0.75D, 0.5D pitch. When it comes to single flights, these are common to use both in feed, like we talked about earlier. They're great pumping efficiency because of the very wide flights. They're typically used in the feeding and the discharge end because they increase the pumping efficiency and will develop a little more pressure. And of course, you're dealing with real high pressure processes, you may have to utilize a gear pump. And so this is when excuse me, when you're dealing with real high melt, or I'm sorry, very fine melt filtration. Maybe you're trying to filter out gels and you're using, really, really small or tight screen packs. The twin screw is not a great pumping device. It doesn't develop or generate a lot of pressure. So in some cases, you can install a gear pump on that machine. It takes the pressure demand off the extruder and puts it on the gear pump. And we look at raw material factors. I'll go through these pretty quickly, but when we think of feeding, one thing to be mindful of is the size of the component you're feeding. This is really more when you're dealing with lab lines, small extruders. So if you're doing recycled material, the large flake, or, just be mindful, it could be too large for the channel on that small machine. Bulk density of powders, they'll tend to fluidize. If they're very low bulk density, you may struggle on feeding. Again, utilizing those high volume elements. High moisture or volatile, you need to take in consideration on degassing. The amount of filler loading and location of feeding. And so again, as I touched on earlier, the high filler loadings can overcool the polymer melt. In some applications, feed location is very important. So when we're dealing with reactive extrusion, where we put the initiator, the activator, and then thermally sensitive additives may need less processing length. So you may need to add those farther downstream. Again, on polymer melting, when you're dealing with low MFI or high viscosity, you can usually melt those in a shorter section. When you're dealing with the opposite, lower viscosity, you may need additional melting length. Again, addition of low molecular weight, so mineral oil, PE, wax, all kinds of lubricant types. Again, will lower that viscosity and delay the polymer melting. Blending of two or more polymers, depending on how different the melt grades. Again, if you're blending or alloying two polymers, quite different on their melt flow. Again, we may take additional process length. And then some polymers very unique, like your ultra high molecular weight PE, TPS, thermoplastic starch, require plasticizers to facilitate polymer flow. Again, mixing is all dependent on what type of mixing you need. Do you need to disperse this additive? Do you need to distribute? That will help you decide what type of elements you need to incorporate. Also, the amount of the additive will determine how much mixing length for optimum dispersion and homogenization. Shear sensitive ones, again, need to be considered. How much mixing length is required without too much shear and risk of degradation. Degassing, one thing that's important is to know, what is the amount of volatile content you're dealing with, the final property requirement. Is it a residual solvent in there? Is it a moisture level? And then the type of volatile that you're dealing with. Now here, this is just an example of a low shear design. This is just to give you some ideas on process conditions. Now here we have a 58 millimeter extruder running 400 kg an hour polypropylene, 100 calcium carbonate. So it's a 80-20 split. And this is just to show you, hey, here's an example of what I would call an underperforming screw. This is not sufficient to really melt and process. Now, you can operate under this condition, But you'll see here, because it's a very low shear design, you're having to run this extruder nearly at the very end of its capability, nearly, 1,057 RPM. Now you can get properties like that. The only problem is you're going to have increased wear and you're going to have a limited extrusion throughput, because if you try to add more material, you're going to have to run higher RPMs to achieve that. This example was just the end of the opposite end of the spectrum. Here I've got a very, very aggressive screw design. And this is kind of an exaggerated one, but just to show you, hey, if I've got a very aggressive, now I'm going to run at a very low RPM. And so here, you can see the extruder torques at 89%. I don't have much room to play increasing throughput and maintaining melt temperature. So again, here, the 215 RPM may not even be sufficient enough for good dispersion downstream on my side feed addition. So here, the optimal design here is, this is a more standard screw design. It's very optimum. And so here you look at this condition, same extruder size, feeding the same formula. Now I'm operating in a more what I'd call nominal process condition. So I'm 685 RPM. I'm only at 35% torque. So I have room to grow in terms of extrusion capacity or throughput without having to run that extruder screw at extreme high RPMs. Now here, this is just an example to throw at you a little bit and say, okay, if I had two guys and I said, hey, I want you to design a screw to run this polypropylene 80%, I'm filling with 20% calcium carbonate. Give me a screw design. So you have the top one and the bottom one, excuse me. And this is just to show, hey, what if I like to use shorter, more aggressive sections on mixing, and someone else might take a more conservative approach that, well, I'm not going to use as many restrictive or aggressive. I'm going to use longer, less aggressive sections. So it's just to show you, really, there's no set rule. Both of these, if you look at the details on the right, you get pretty well equivalent results. I mean, there's 2-degree difference in temperature. There's almost non-detectable specific energy input. The resonance time similar, torque similar, the extensional stress, which is in the apex region, and I'm looking at mixing section 2 and 3. They're almost identical. So your properties are going to be exactly the same. So it's just to demonstrate here that, there's flexibility in the design. It all depends on your processing window. Most applications have a window to operate in, of course. Some are broader than others. You can get by with, 3 or 4 different designs. They all may work, but it may take some time for an application that's a little more critical and a little more narrow processing window to really drive down on that screw design. But this is, again, just a good example to say, hey, I like to use shorter mixing sections that are a little more aggressive. I'm using larger right hand. I'm using a little more restrictive elements in that top example, because I've got reverse kneading and reverse conveying in all 3 locations. But down below, maybe another person takes a little more conservative approach, says, well, I'm going to use neutral and reverse kneading and less of the reverse conveying and so forth. So again, same results. Now we look at restrictive elements. And again, as I mentioned, neutral, 90-degree, and your reverse kneading. Here you can see I'm running the same processing conditions. The only difference is on the bottom example is I've got more restrictive elements in here. So the top example, I've got a neutral 90 at the end of the second mixing section, and then I've got a reverse kneading at the last mixing section. On the bottom one, I've got reverse kneading at first, second, neutral on the third, and reverse conveyor in the last one. And you can see there's a little difference. I mean, obviously the restrictive elements, you see the melt temperature is 5 degrees warmer, a little more work in the material, and a little more resonance time, because those restrictive elements, it increases the amount of time that material spends in that localized melting or mixing zone. So it imparts a little more work into the material. So just know, placing those restrictive elements where you put them along the process, you're always going to increase time. Now, when we talk about these restrictive elements, and you go from neutral to reverse kneading to reverse conveying, always increases the intensity of the mixing, because the neutral, of course, has more, 90 degree has more space between the lobes, so it allows more leakage flow, so it doesn't hold the material back as well. My reverse kneading is forcing the material back upstream, so it's going to be more restrictive. My reverse conveying, remember, has a solid flight all the way around 360 degrees. There's no gap or spaces like the kneading blocks have, so the leakage flow is forced to go over the flight between the barrel wall and the flight tip, so it is the most restrictive. Now we look at reactive extrusion. This is a TPU polymerization. And here we're going to look at residence time. And so you can see here, I'm running this process conditions the exact same. Both are operating at 300 kilograms per hour, 275 RPM. I've got the exact same mixing elements on both of these screws. Nothing changes. The only difference is in the top example, between the mixing sections, I'm using 60-60 conveying elements. And in the bottom, I'm using 30-30. And so this is a polymerization reaction. So time is important in this aspect when it comes to polymerization, to allow those monomers to react. So when you want to control time, you want to increase the amount of time. Maybe in that top example, you're not getting enough residence time to complete the reaction. So you can simply switch those SE from 60-60 to 30-30. Remember, the shorter pitch creates less axial displacement per revolution. So you can see here, I went from 30 seconds, almost basically a 50% increase, right? From 30 to 46, a little over 50% increase in residence time, just simply changing to those lower pitch conveying elements. So here we go. I've got Christian on standby. Christian's gonna try to pull up a poll. So here we go with a 52 millimeter extruder, polypropylene, 10 MFI. It's just a polymer only, 400 kilograms per hour, 600 RPM. So I've got screw A and screw B. And what I'm noting here is the only thing changing are the blue elements, which is the right-hand kneading. You can see here all my restrictive elements on this screw are the same. So I've got 90, 548, same thing, 3216 left hand, 45 524 left hand, so forth. All those in red I've designated, the restrictive elements are all the same. The only thing changing, the top screw, I've got a 30 degrees 7 lobe, 48 length. In all of those right hand positions, whereas on the bottom screw, the only difference is a 60 degree 4 lobe 24. On the left here, you'll see under each screw A, I've got the lobe width. So you can see my 30 degree is 6.85 and my 60 degree or 6 millimeter lobe width. So the question is, which screw will generate the higher melt temperature? And so take a look at this, see what you think, and see what kind of results you're thinking here, which screw will generate the higher melt temperature.
Hey, Daron, can we squeeze in a quick question while we let the
Sure.
Sure. When determining the type of screw elements to use, do you take into consideration L/D?
Yes. I do, mainly when I'm trying to scale. That's important. When you're scaling from machine to machine, that's where I focus on L/D. So for example, if I'm going from a lab line and I have a mixing section that, let's say it's 2.5 L/D total length, I'm going to try to match that on my production machine. And I'm going to take each individual element and it's L over D. So if I'm using 1D elements on the 24, I'm going to try to use those 1D on my larger machine. So yeah, predominantly on scale up. And I will do a webinar later in the year. I can't remember if it's in September, but I do one on a scale up and transfer of applications from machine to machine, and we'll dive pretty deep on that topic.
Okay,
So.
all right. And then how did you calculate the power consumption along the axial length as a function of the screw element?
Oh, and the one that had the 79%? Yeah, I think that graph that I had that showed the 79%, that was on the simulation software I used, so it shows the power input along that process section.
Okay. All right. Well, for our poll, so do you want to, looks like we had 59% select screw B and then 40% select screw A.
Ah, okay. So 40%, you said 40% chose A?
Correct. And
Okay,
then,
good.
well, now it's up to 42%. So, and then 58%
Oh, somebody
screw B.
changed their answer last minute. Okay, now that's fine. Okay, so let's move forward. And so, great job, because majority sided with screw B. And so, yeah, there's not a big difference here, obviously. I mean, we're talking 2 degrees, if that. But here, this is what changes. And this is what kind of we touched on, and I wanted to, that was kind of the point of this. And yeah, there is a little different lobe width difference in the 30 and the 60, but not enough. The main thing here is, remember that the 30 degree is primarily pushing the material through the machine. And so it's moving forward, and there's less leakage flow in the upstream or back against the process direction, whereas the 60 allows more leakage flow because of the larger gap between those lobes. And so when that material leaks back upstream, again, it spends more time in that localized area, so it's allowing a little more time to work that material. And you can see I even put the residence time here, 7.4 seconds. So it's not much. It's not even really distinguishable, to be honest. In a process like this, if you had these two screw designs, you'd probably see very similar, same properties. But it's just to kind of demonstrate for you that that lobe stagger angle and how it influences that process in terms of leakage flow, residence time, and the amount of work. So again, no, that was great. And that concludes the webinar. If there's any other questions, Christian, I'll turn that over to you.
Yeah, we have time for a couple more. Which metallurgy is best suitable for screw elements for reactive extrusion and conventional extrusion?
I don't know if there's really a key difference. I mean, the main thing, of course, to understand is what are your reactive components and are they corrosive? That would be my suggestion. So it would really depend on the type of additive, what type of monomers or reactive components. Typically standard, it really depends on the application. So when you're dealing with glass filled, of course, real abrasive, high abrasive type stuff, silica, glass filled, usually requires a higher abrasive resistant metallurgy. Now, when you're dealing with corrosion, then it changes a little bit. Now, we offer metallurgy for all types of applications, not only, geared more for abrasive versus corrosive, or both. So, yeah.
And then to go back to earlier, what is meant for 45/5/30?
Yeah, what that is you're on the KB nomenclature, the first number is the stagger angle in the lobe. So like KB 45 is 45 degree tilt from one lobe to the adjacent or next downstream lobe. 5 is the number of lobes total on that element, and then 30 is the total length of the element. So 45/5/30, and each individual lobe is 30 divided by 5. They're 6 millimeters. So, yeah.
Okay, great. Thank you, Daron. And there's been a lot of interest in this PowerPoint to be shared. We just asked you to use it for training purposes, of course. and you can reach out to me at christian.davis@cpm.net, and I can help you with that. Or you can always reach out to Daron directly at daron.fraim@cpm.net. And thank you, Daron, and everyone who joined us. A recording of this webinar will be available on 1cpm.com within the next week or two, where you can also find all of our previous editions as well. This concludes today's webinar. If you have any questions or would like more information on what CPM can do for you, please also email us at extrusion.sales@cpm.net. Thank you.